Hey dear programmers, how are you doing today? Welcome to the channel, and topic of this video is Introduction to Python NumPy. If you are using Python for data science or mathematical computation, the chances are you have already heard about something called NumPy. It's one of the most widely used, popular and very powerful library module for Python. And if you are planning to do any work in data analytic, machine learning or mathematical computation, this is one library you should definitely look for, and this video intended to help you understand what this library can do for you. Okay, so these are the 6 topics we are going to look into in this particular video. It starts with the very basic question which everyone asks before learning NumPy is why NumPy and not Python list. Second is how to create NumPy arrays. Third is about memory footprints as compared to Python list. Fourth is about creating n-dimensional arrays in NumPy. Fifth is the biggest USP of NumPy is how to do mathematical operations on NumPy arrays. And sixth and last will be the element lookup. By the end of this video, you will be fairly comfortable with NumPy. So let's start. First thing first, let's start with why NumPy and not Python list. Frankly friends, there is nothing in NumPy which you cannot do in Python list, or for that matter by using any another data structure. Still, you should consider NumPy because NumPy provides efficient storage and better way of handling data for mathematical operations. Yes, NumPy is meant for mathematics. Now what I'm gonna do in this particular video, that along with creating NumPy, I will also create a Python list, and you can just compare between these two and judge yourself. Now come to our second topic, how to create a NumPy array. NumPy array is created by calling a function called array in NumPy module. And to call that function, you have to import NumPy as np. So I've imported NumPy, and if I want to create a NumPy array, I'll do np arr equal to np dot array, and I'll define a list 2 3 4 5 6 for example. This is the way I create my NumPy array, and if I just go ahead and print my NumPy array, we'll see an output similar to Python list. Similarly, I can create a Python array like this 1 2 3 4 5 6, and if I just display Python array, it will display similar to what is being displayed with NumPy. Now on the look of it, there is not much difference between Python array and NumPy array. The only difference seems to be I'm calling a function. But let's start exploring things one by one. NumPy arrays are meant to be homogeneous. This means that in the Python array, if I change one of the element from integer to string, the first two will remain integer and hello will be string, and 4 5 6 will remain integer. But what will happen if I do the same to NumPy? So I'll go ahead and create the NumPy array over here again, and let me just print the NumPy array, rather than just display what is the content of NumPy array. It's arr. NumPy arrays are associated with a particular type. All the elements of the array will be of same type because NumPy is homogeneous. So let's see what is the type over here. So if I just print np underscore arr dot d type is data type. It will say all the elements are of int 64. But if I change one of them as hello, see here, see what had happened. The data type changed to a Unicode string type, and all of them are converted into a string. The first difference between Python array and NumPy array is this. In Python array is meant for heterogeneous element, but NumPy arrays are not. It will always be homogeneous. Things get interesting if I just create a 4 over here instead of hello. See what happens. Still everything remains Unicode type, even if it's possible to change 4 to an integer type. And if we put integer, everything will be integer type. And if I go ahead and change one of them as floating point, everything will be a floating point. So NumPy arrays are meant to be homogeneous. You will ask, what is the reason for being homogeneous? This is the way how mathematics works. NumPy arrays are not meant for creating just list. It is meant for creating n by m arrays, which is equivalent to matrices and tensors in computer science. And if you do any mathematical calculation on matrices and tensors, all of them are of same type. Now let's talk about memory footprints. I'll again create the same NumPy array and I'll again create the Python array. Okay, so far so good. But I want to know what is the memory occupied by both elements of Python array as well as NumPy array. To know the memory of elements occupied by Python array, I need to import a package called sys, and I'll have to say sys dot get size of an element. So if in this particular case I am taking the size of an element which is an integer, it can be any integer 1 or 10. So it says get size of one integer is 28. Now to know the amount of memory occupied by Python array, I can multiply this with len of pyarr. So len pyarr gives me a number of elements in the list. You can say it's 168. Now in case of NumPy array, I have a member variable called item size. This gives the amount of memory occupied by one element, and if I multiply this with NumPy array dot size gives number of element in the NumPy array, it gives you 48. So look at the difference between size of Python list and NumPy array. It's a huge difference. That's why if you have to load lots of matrices in the memory, big size data in the memory, you should use NumPy. Now if this difference is not intimidating, we can do further optimization in NumPy array. I can define a data type over here. For example, in this case, I know that all of my elements can be stored in single bytes. So I can just say data type is np.int8, 8-bit single byte. So in this particular case, see the size difference. Now using only 6 bytes of memory as compared to 168 of Python list. So this depicts the saving that you get with NumPy. Not only integer types, the saving is also for floating point types. Let me create a NumPy array with floating type float 64. Okay, so if I just print nparr, you know it will the type is floating point. Okay, because it can only be homogeneous, and this is the way we define the data type. Okay, and if you just print, you can see that it's 1 decimal, 2 decimal. For Python array also I can create a floating point list, say 1 dot, 2 dot, 3 dot, 4 dot, 5 dot, 6 dot. And if I just go ahead and print it, okay, look into the amount of memory occupied by this Python list. It is still 168, while if we go ahead and see the amount of memory occupied by NumPy array is 48. If we change this float 64 to float 32, the memory saving will be much more. Now it's only 24. And it is true for a string also. For that matter, let's say I convert this into str type. So I have a string type now. And similarly, let me create a Python array also with a string type. Okay, I have created a string type. Now everything is a string type. Now when you check the size of NumPy array, it's 24, and if I go ahead and check the size of Python list, it's 168. So memory footprint savings is not limited to integer or floating point. You achieve the same with strings also. That's why NumPy is better as far as memory footprints goes. Okay, now let's go to our fourth topic, which is about creating n-dimensional array. So we can also create n-dimensional array using the same array function, but we have to pass n dimension. I have just copy paste a n dimension thing. This is how I have created an nd array. If I just go and print np array, you will see it's a 2-dimension array. It's a 2 by 5 matrix. Okay, similarly I can also create Python array of the same type, and if you just go ahead and print py array, you'll see the 2-dimensional array. Once we have created these two array, okay, they are similar. Apart from memory saving, what else we get? Well, with NumPy arrays, we can change the dimension of array at any point of time using reshape function. For example, I can say np.arr and I call reshape. So as of now I have 2 by 5 matrix. I want to convert into 5 by 2. Done. I have converted this into 5 by 2 matrix. So it's not limited to multi-dimensional matrix. I can create 1 by 10 matrix also, or for that matter 10 by 1 matrix also, like this. So it's easy to change the shape and dimension of the NumPy arrays. Now one thing we have to be careful about, the multiplicity of these numbers should result in number of elements that was there in original array. If we change this, then it will be an error because it is not able to find it, or let's say 5 1, it will not be able to completely change the shape based on number of elements. So multiplicity matters. Once you take care of the multiplicity, you can change the shape. Okay, now here I have passed number of elements 1 2 3 4 5 6 7 8 9 10 in NumPy arrays to create a multi-dimensional array. But every time you don't want to do that, you want to generate a NumPy array with some predefined value. How to do that? You can do that using arrange function. So what I can do is that npar equal to np.array, arrange, and I say generate me a number between 0 to 10. And if I go ahead and just see what is being generated, you know the number is generated between 0 to 10. It inclusive exclusive, which means it includes 0 but exclude 10. And as you can see from the end result that the step is actually 1. And this step can be changed. I can change the step as 2. In that case 0 to 4 6 8, and this can be decimal also, and in this case these many numbers will be generated. Let the step be 1. Not only this, we can also change the shape of array as we did earlier by using reshape function. Let's say 10, so 5 2. So this is how we use reshape along with arrange. One thing we have to be careful about, that this line of code doesn't change the shape of original matrix. So if you just go ahead and print nparr, it will remain 1 by 10. But in this particular case, it generates a new matrix for us. So np new equal to this. And if I go ahead and check np new, and we see 5 by 2, so it doesn't change in place, and it always generates a new matrix when we do that. Now what if we want to generate ones and zeros? These are required when we want to create a dense matrix or a sparse matrix, or for that matter initialize all the value with a predefined value. One thing you can do with np.empty. So let me create nparr equal to np.empty, and again I say I need 5 by 2. Okay, sorry, I have to give double over here. Okay, and if I go ahead and print nparr, you can see 5 by 2 matrix is created, but the values are pretty much scrambled kind of values. So here also you have seen a floating point value, but you can change the data type as np.int32 and you'll see integer value. So as you have seen here, it's saying 0 0 0. It also provides some very unpredictable values. So if I say 52, I mean you can see some unpredictable values are there. Okay, so let's go back to 5 2. Okay, now there are another two functions which you should be using most of the time, is zeros and ones. So as its name suggests, zeros means it will always create array with a particular dimension with all zeros in it, and ones will create a array with a particular dimension with all ones in it. So if you don't provide a data type, by default ones will generate a floating point value. Now we have seen that reshape changes the shape from any dimension to any dimension provided the multiplicity factor meet. The rival is opposite. It converts any dimension array into a one dimension array. So nparr dot ravel, you can see we have generated one dimension array from 5 by 2 dimension array. Now let's talk about the biggest USP of NumPy, the mathematical operations. To understand this, let me create a PyARR, a small array 1 2 3, and let me create a NumPy array also. nparr equal to np dot array, let's say 1 2 3. Okay, and just printing PyARR, and here I'll printing nparr. So what will happen if I multiply both the arrays by 2. So in Python array, you create a duplicate set of values, but the NumPy array actually multiplies the 2 with all the elements, and this is how matrix operation work. So Python arrays are not good for doing mathematical operation because it cannot do it. Similarly, if I just add by 2, sorry, I cannot add Python list by 2, so I cannot add anything over here. But let me add something by 2 over here. So you can see that all the elements 2 is being added, and this is true for single dimension as well as for multi-dimension array. For example, let me create a NumPy array as np.ones, and I want say 5 by 2, and let me see if everything is generated fine, and it's a 5 by 2. And if I multiply by 10, see everything is multiplied by 10. If I add 10, everything is added by 10. This is the reason why NumPy arranges scores in case of mathematical calculation, because it behaves as if doing the calculation and mathematics itself. And that's the reason it is one of the biggest USP of using NumPy. Now let's come back to our last topic, which is called elements lookup in NumPy. So there are various ways of looking elements into the NumPy array, but most likely you are gonna use where non-zero or count 0. Let's see each one of them. So for that, let me create a NumPy array as nparr, and I have a list with values, let's say 1, 2, 3, 4, 5 for example. Where represents a case, which means that it will return me things where the condition turned out to be true. So if I say np.where and I say np underscore arr is greater than 2, it will return me the indexes of all those elements where the array elements are greater than 2. So for example, let me change 12, 15. It will return the index. It will not return the elements. It will just return the index. Similarly, we can also use non-zero to count number of non-zeros in the NumPy array. So if I say np dot non-zero and let's say nparr, it will also return the index of all the elements which are non-zero. For example, 0, 1, 2 is 0, that's why it is not returned. It will return the index of all the elements which are non-zero. The non-zero kind of function is extremely useful if you want to check whether it's a matrix is sparse or dense, or what is the density of particular matrix. Another function which you would likely to use is count non-zero. So if I say np dot count non-zero, this is different than non-zero function in a way that what is the output in this particular case. So count non-zero is actually count underscore non-zero. So in this particular case, it just returns the count of number of value count. It doesn't return the index. That's the difference between this non-zero and count non-zero. So you can see that there are non-zero 4 elements. If I increase the non-zero from 4 to 5, it will return me 5. So that's all about the basic usage of NumPy. I hope you are now comfortable with using this NumPy, and we have covered all these 6 topics. This is what you need for basic understanding and usage of NumPy. I'll also create a video on specific tips and tricks for advanced usage of NumPy in next couple of weeks. Till then, thanks a lot guys. Thanks for watching. Please do not forget to like, subscribe and share. It's all about your encouragement. Thank you. Thanks for watching.